Thank you for introduction. Good morning, ladies and gentlemen. The name of presentation that I would tell today is Wings for UAV based on high-lift aerofoils. This work continues the results of joint project, joint work, that Israel Aerospace Industries provided together with aerodynamic team of ADE. Let's begin from some historical review. Here is the picture from well-known book, but not new book. This is the release of 83 year. So you see that for low readiness areas that relative to the wings of unmanned vehicles, we don't see even the names, even the bit about the UAV. And the modern releases, the modern reductions of the same graphs already continue the UAV and already continue even the pictures. This is the pictures from open sources from internet. You see that UAV is related for the readiness number area, the main aerodynamic parameter readiness number, that corresponding to our investigation, about 300K. This is a number that we'll speak today. And for additional sample, this is not historical review, this is a forecast, the American market of unmanned vehicles. This is the modern time, and this is a forecast for the next decades. So you see the increase of market, and this is the reason of our interest to this area of investigation. Our Israel aerospace industry is one of the leaders, and the last decades we are going in for researching in unmanned vehicles, the well-known vehicles that now in employment all around the world is the Heron family, the Heron 1. It's already classic, based on two-element aerofoils and high aspect ratio aerodynamics. And the modern, the larger version is Heron TP. I want to put your attention on the view of these aircrafts. The external payloads, the non-stream fuselage, and these vehicles were created not for speed flight. It's clearly seen on these pictures. This is important for our today analysis, and it's clearly seen the high initial drag of these configurations. This is not a mistake. This is reality for tactical operational UAVs. If we look for new generation of unmanned vehicles of Israel aerospace, this is a Panther family. The Panther family, the full-scale Panther family, and mini versions. This is outstanding aerodynamic and flight control, and this is a converter for vertical takeoff and landing, and for horizontal flight as well. But you see that these vehicles consider three engines, and pop up. So the sole problem, the high initial drag, not flight speed aerodynamic. This family, the Panther family, is lying close to our area of interest. The speeds that you see here on the slides is correspond to the readiness number that we discussed today, that we made investigation. Let's go to analysis. This is one of the main aerodynamic factor for tactical UAV is endurance. We not analyze today the engines parameter, the fuel, and the structure, only aerodynamic parameter, and the main aerodynamic parameter is aerodynamic endurance factor. Because of the exponent 1.5, the lift of aircraft became the most important parameter, even mostly than initial drag. But let's compare the aircraft sailplane with very clean aerodynamic and conventional tactical operational UAV. We see that for clean configuration, to achieve a maximum aerodynamic endurance, we do not need the high level of maximum lift. But if we come for real application with initial drag, this is empirical method and measurement about 150 counts, to achieve the high value of endurance factor, we need to increase lift, as high as possible, and so we'll get the aerodynamic gain. On the right graph, it's presented the comparison between two-element airfoil, between wings based on two-element airfoil with high aspect ratio. This is sample from Heron family. In comparison with conventional single-element based wing, for example, the same class is Predator. And it's clearly seen that for clean application, two-element wings, high-lift wings not have preferences, but for real application with external payloads, with high initial drag, the high-lift wings became the gain. If we retain this analysis for Panther family, that is more clear for our today investigation, we see the same results. For clean configuration, for example, with 200 counts, we see some moderate lift. We need to achieve maximum lift. But if we look for real configuration, to achieve maximum value, high value of aerodynamic endurance, we need to increase lift as possible. But it's not enough to create wing with airfoil based on high lift sections. It is very important complex wing design, including high aspect ratio. On the right graph, we see that for low aspect ratio, the maximum value of aerodynamic endurance is lying not in the high lift area. So high lift airfoils cannot help us for wings with low aspect ratio. But with high aspect ratio, with special long endurance design, the aspect ratio and high value of maximum lift assist us to achieve higher value of aerodynamic endurance. The low speed that is characterized for unmanned vehicles and limited dimensions because of miniaturizations of electronic and miniaturizations of plane relates to the low values of Reynolds number, and this brings the new difficulties for wing design. On this graph, we see that higher value of lift, high lift flight, provide the decrease of Reynolds number because of decreasing of flight speed. And this brings the special features of low Reynolds wing design. The main problem of low Reynolds aerodynamic is that we not put attention for higher Reynolds number, for transonic, for speed flight, is the laminar separation bubble. The laminar separation bubble is the feature of transition between laminar and turbulent flow, and the good design provide the minimal size of separation bubble and full flow reattachment after the separation bubble. But unmistakable design continues the danger of burst of separation bubble with early transition to fully turbulent flow or to fully separation. So we can lost the lift and decrease the capabilities of our wing. And on this graph we see that the area of our UAV is lying on really critically value of Reynolds number. So it is very important the careful design of airfoils and of wing for this area of speed flight. And now we became some report about the results. Several airfoils were designed. Every airfoil was tested in wind tunnel in Kanpur, Indian Institute of Technology. Every airfoil belonged to the original concept, and every airfoil belonged to high lift concept. How we can to achieve maximum value of lift? Let's begin from single airfoil. The main way to increase lift value is camber shape and strong bluntness of leading gate of front part of airfoil to achieve to increase the flow acceleration on front part of airfoil and to provide place for full recovery. Additional concave for additional lift, but the price for this will be additional pitching moment. And this is permanent curvature design is to provide a mild stall. The same principle is for two element airfoils, but here we have additional level of difficulties, the design of slot. This is a two element airfoil with permanent slot, and we must to carefully design the slot as a confuser, not only for nominal setting, but it have to work as a confuser for all flap deflections. Here must to tell that conventional computational tool cannot assist us to predict horizontal overlap and vertical gap, and so this design is only from empirical experience, and we have to provide reliable overlap for all flap deflections. The new generation is two-element aerofoil with retractable flap, the so named as fixed hinge aerofoil. This is a part of class of Fowler flap, but the second element not go inside as for general aviation wing. This is only retracted to main body. The special feature, the special difficulty of design here is to design the bay for retracted flap so that for flight with retracted flap, wing can work as wing based on single element airfoil. This airfoil provides not only positive flap deflection, but as well the Hort increment. So because of movement, second element afterward. So we get the additional value of lift. The single element airfoil B90 was designed and tested and in wind tunnel. We see the good agreement between experiment and computational lines, and we see the wide milestone plateau, but limited value of maximum lift. Some reserve of increasing of maximum lift could be achieved by additional devices, such as DTE, divergent train leakage, or we proposed the simplified version of DTE, the weight train leakage, that will be more simple for production. But even with this device, the maximum lift retain limited. So to achieve the highest value of maximum lift, we propose the two-element airfoil with built-in possibility of adaptive geometry, with positive for flap deflection, and even for nominal setting, we get the high value of maximum lift and high value of loitering lift, including strict restriction of flight speed safety. The negative of this concept, not negative but some disadvantage, is drag penalty, because two-element airfoils always provide the higher drag with comparison with single-element airfoil. To minimize drag for maximum speed flight, that is more important, we can use decambering options to fly with negative deflection of flap, but even in this case, we retain is relatively high value of drag. The new proposal is two-element airfoil with retractable flap. The deflected flap, not only positive deflection but movement to backward, we can to achieve the higher value of maximum lift, and we can to fly it with retracted flap with drag the similar as the single element airfoil. But we have to pay some price for these advantages. This airfoil is suitable only for positive deflection, so it can be applied only as flap section, not as aileron section. And I put your attention to position of hinge point. It requires the higher power of actuators, higher hinge moment. Sometimes we have the limit of actuators power, so it could be some difficulties. Let's compare the presented designs, the presented concepts. Here is all three concepts on one picture. We see that two-element airfoil with retractable flap in the version of reflected flap provides the maximum lift from all three ways. This is the maximum lift, and this is the loitering area. So we see that fixed hinge airfoil provides the maximum lift, the maximum endurance, maximum aerodynamic endurance for loitering flight. If we look on drag polars, and we are speaking about the Reynolds number 300, that is intermediate, that is relative to small size or even medium or mini size of UAV, we see that airfoil with retractable flap provides the minimum drag value as for deflected flap, and especially important, more important, the drag for speed flight for airfoil with retracted flap will be similar as for single element airfoil, and less than for slotted two-element airfoil, even with the cambering option. What is the main goal of our airfoil design? The main goal, of course, is not only our interest, but the design of complex wing, of complex high lift wing for long endurance UAV. Let's look of presented airfoils. All these airfoils belong to the one family. So it is they all have the same geometry of front part, and this is allow us to employ these airfoils as a Lego, as some set of wing section to create high lift complex wing, to create a complex high lift wing. How option we see? We see, of course, option the wing based on single element airfoil. This will be high lift airfoil with comparison with conventional catalog airfoils, but it is not enough lift to achieve high value of aerodynamic endurance. So we can to use the two-element airfoils as the aileron section, and single element airfoil as the inboard section, and this way we can to retain full flight control because of high level of maximum lift for outboard wing. We try to retain full flight control and to use maximum lift as the point of fly without safety restriction for internal wind because of mild stall effect of designed aerofoil. But this decision we still retain on moderate maximum lift. And the new proposed is the high lift wing with maximum achievable level of lift. For internal wing, for inboard wing, we propose to use two-element aerofoil with deflected flap. And for outboard wing, two-element slotted airfoil. So we can to use the deflected flap as a flap for takeoff and landing for achieve maximum lift, and for loitering flight we can to fly with relatively low drag with retracted flap. And as the aileron section, we propose to use slotted two-element airfoil with built-in possibility of adaptive geometry, so we can to gain not only the maximum theoretical endurance factor aerodynamic, but the aerodynamic endurance for real mission, as for loitering fly, as for speed fly, because of some drag economy. And what will be the conclusions? Some summaries. Several high-lift airfoils were designed. Every airfoil was experimentally tested, and wind tunnel test were confirmed the high-lift capability of these airfoils. Every airfoil belonged to original different concept, and every concept has right to be applied for small, medium, and mini size of UAV. So this is applied investigation, not only theoretical interest. All designed airfoils and all proposed versions of high-lift wings are suitable for small, medium-sized UAV. And the new concept, the new complex high-lift wing were proposed, and it will be interesting to apply this wing to get the maximum high-lift capability and the maximum aerodynamic endurance. At the end, possible the most important slide, the acknowledgement. I want to use possibility to great thanks for wind tunnel facility staff in Kanpur Indian Institute of Technology, for all staff, and personally for Professor Padar, for support, for assistance, for contribution. As I told before, this work was joint work with ADE aerodynamic team, and great thanks for aerodynamic team, for Mr. Selvaraj, Sankar, Baunit, for collaboration, and except that, for really warm relation. It was nice to work with this team, and I hope I can to tell that to be continued, that we will to be with a new joint product to continue our collaboration. Thank you.
A couple of questions, please.
Hello, can you hear me? I'm Vishwanath from Boeing, India. We saw very nice, interesting results and the comparison between slotted as well as the hinged aerofoil with a flap. Just two general comments. One has to do with the fact that all the high lift characteristics on these aerofoils are typical. How sensitive are they to off-design conditions? Because there's a whole lot of viscous flow phenomena on the wing, including the laminar separation bubble. The second question has to do with if there is no bubble on the aerofoil, you will have a laminar flow extending to 30, 40, 50% chord. And there has been a general practice when you look at NLF aerofoils that you use a tripping mechanism so that it does not naturally trip at 50-60% chord, but it trips at a designed position so that you take advantage of the turbulent boundary layer pressure recovery.
Yeah, okay. Okay, this one. Okay. Next. The first question. We are always design our airfoils, our wing. We are try to always want to avoid solenoid point design. We are always design our airfoils to provide full flight envelope from the level of maximum lift and from the level of speed flight. All these points were tested experimentally. All these points were carefully analyzed during the design. So all these airfoils that presented today are not point design. This is one of advance of this design that they provide full flight polar. This is very important for real application, of course. And once more, we are always avoid the point design way. The other question, because of short time for presentation, I am not present on graphs the comparison between fully turbulent and laminar airfoils, but of course, the design airfoils was checked for fully turbulent behavior as computational as in wind tunnel test. Of course, we pay some drag and some decrease of maximum lift for fully turbulent airfoil, but even with fully contaminated, strong contaminated airfoil, we retain the high value of maximum lift. For example, if I remember, for fully turbulent airfoil, the maximum lift will be approximated here. For clean configuration without additional trailing edge device. And for two-element airfoil, there will be maximum lift something in this area for two-element slotted airfoil. The test was very high value of test with strong contamination, with slight contamination. We tested and analyzed airfoils computationally for light contamination and for fully turbulent behavior. So once more, we are retained on high lift design for fully turbulent wings.
Any more questions? One more question probably we can take. Mike, please.
The pivot model, was it modeled as a solid or as a complete solid?
This is a solid.
So what was the difference between the analyzed and the real practical results?
We got a good agreement in experiment, a good agreement with our computational results. Because the solid, because it is interesting to try some non-conventional ways, but because the main goal of our investigation is real application designed for real UAVs, so we always simplify our design, so not to go to complexity of production.
Thank you.
Okay, I think we can close this. The first talk, I think Dr. Alexander Nagel addressed the advantages of multi-element airfoils, both the permanent as well as retractable ones, and where to use what kind of multi-elements have been addressed. And I'm sure that people will take the advantage of this in all our designs of UAVs. And I take this opportunity to thank Dr. Nagel for his excellent presentation.
Yeah, just